Okay, let's solve this problem. The last time we determined U1, H2, H3, and U4. So this time we are going to determine the cutoff ratio. I'm sorry, the compression ratio R, which is the volume ratio between the top dead bottom dead center and the top dead center. So V1 divided by V2. And the cutoff ratio, which is the volume ratio between number 3 and number 2. So R of C is V3 over V2. And the thermal efficiency, which can be determined by 1 minus Q out over Q in, and the mean effective pressure, D, is mean effective pressure can be determined by net work divided by V1 minus V2. So let's do that. First of all, this compression ratio, I think we already found this compression ratio, is here V2 over V1 is VR2 over VR1, and we already know VR2 over VR1. This is 6.21. I'm sorry, 621.2, this one, divided by VR2, 26.793. So if you do the calculation, you get 23.19. Okay. What about cutoff ratio? V3 over V2. I think we already calculated V3 over V2 somewhere or here. V2 over V3 is T2 over T3. So this is going to be T3 over T2 according to this one. And we already know T3 2150 Kelvin and T2 979.6 Kelvin. So you can determine the cutoff ratio 2.19. What about this thermal efficiency? We already studied the energy balance equation that has Q in and Q out. By the way, Q out is the heat rejection after this power stroke. So Q out is Q421 divided by Q in is after this compression process. So Q23, this is when it goes in, this is where it goes out. Q23. And we can calculate this by 1 minus U4 minus U1 divided by H3 minus H2. The energy balance equation that contains Q3 and H3 minus H2, Q41 is U4 minus U1. We already studied these energy balance equations last Tuesday. So if you do the calculation, you get 0.597, which means 59.7%. The last one is mean effective pressure. So W net can be determined by Q in minus Q out, according to the energy balance equation in chapter 5 for heat engine. W net is Q in minus Q out. You may remember, if you go back to chapter 5, And then Q in is Q23. Q23 minus Q out, Q41, divided by V1 minus V2. So how do you calculate Q23? It's going to be mass times H3 minus H2 minus mass times U4 minus U1 divided by let's take mass out of it. Mass times V1 minus V2. Then we can cancel mass out. Then the mean effective pressure can be determined by H3 minus H2 minus U4 minus U1 divided by V1 minus V2. Do we know V1? We can calculate V1. So V1, if you take V1 out of it, it's going to be 1 minus V2 over V1. Then we have H3 here, 2440.3. H2 here, 1022.82. U4 here, 785.75. U1 here, 214.07. And the compression ratio, the inverse of compression ratio, which is 1 over 23.19. 1 over 23.19. What about V1? We can calculate V1 from ideal gas equation. V1 is RT1. And P1 is given 95 kilopascal. R is the gas constant for ideal gas of air, 0.287. T1 is 300 Kelvin. So we get V1 goes here. So if you calculate mean effective pressure, we get 975 kilopascal. So that's how you solve this problem. Once you determine U1, H2, H3, U4. So basically, what you are going to do in the final exam, if I give you, let's say, Otto cycle or diesel cycle, you need to determine the thermal properties at each state. Let's say U1, H2, H3, U4. So once you find them, and calculating the other is going to be not very difficult. But if you miss one of them, it's going to be change all the values on the right-hand side. So the way I'm going to grade this problem is going to be whether you get each thermal property right or not. So if it is 10 points, it's going to be maybe 2 point, 2 point, 2 point, 2 point, and the entire is going to be 2 points. Otherwise, if you miss one of the, the thermal property, it's going to change all the values on the right-hand side. Okay. Oh, this one? Yeah, $20 per page. I was kidding. So that's everything about diesel cycle. We have one more cycle, which is gas turbine, or sometimes we say Brayton gas turbine, or just Brayton cycle. So basically, this one looks similar to Rankine cycle that we studied in chapter 8. And we use this gas turbine, the most likely in a power plant. However, there is one difference between gas turbine power plants and vapor power plants. By the way, vapor power plant means the Rankine cycle. The main difference between gas turbine and Rankine cycle is that in the Rankine cycle, we use water. So we use steam, it goes to saturated vapor, superheat vapor, and goes to saturated mixture and saturated liquid, compressed liquid. So we have repeated phase change of water when we use a Rankine cycle. So we rely on the phase change of water. So in that case, the Rankine cycle consists of boiler, turbine, and condenser and pump. So 1, 2, 3, 4. So we have phase change between here and there, super vapor or saturated vapor. It becomes saturated mixture. It becomes saturated liquid and compressed liquid. So we have a repeated phase change. And we use the phase change of what? Water. But there's one limitation in water, which is that if you remember PV diagram or TV diagram, the saturation curve looks like that. And what is it called on top of this? Critical point. So what happens when the temperature goes beyond this critical point? Water does not exist as vapor, liquid anymore. So above this temperature, above this critical point, water exists as supercritical water that has the characteristics of liquid and vapor together. Then, when you want to use this supercritical water, what is the problem? Because it has the characteristics of both, controlling this water in a power plant is going to be very challenging. So when we use a Rankine cycle, we are trying to limit the maximum temperature of water below the critical point. Then, if you do that, what is the problem? If you remember the heat engine, how do we determine heat engine efficiency? The efficiency is 1 minus Q in over Q out, also the other way, Q out over Q in. What is the ideal efficiency? The Carnot efficiency can be determined by 1 minus TL over TH. So this is a simple way to determine the thermal efficiency of an environment. So what is TL? TL is the temperature of the coolant. So this can be the temperature of river or lake or ocean, sea, so where we use, the coolant coming from. And what is the other one? The temperature at the inlet of the turbine, the temperature of the source. So if you want to improve the thermal efficiency of the system, there are two options. One, you can decrease the coolant temperature. So if you decrease the coolant temperature, the thermal efficiency goes up. So how can we do that? Don't build a power plant here, build a power plant maybe in Alaska. Then the efficiency goes up. So is it always a good option? No, we need to use electricity right here. We don't want to, the transfer electricity from all over there, because there is an energy loss. Transferring, the electricity is significant. So this is not an option. Then what is the other option? We can increase the temperature of the energy source. How can we do that? We can burn more fossil fuel. We can rely on nuclear reaction. So obtaining high temperature heat is easy. However, using this high temperature is limited by the working fluid, which is water. So because of this, we cannot just increase the temperature of the source, because water cannot survive at high temperature. Then what can we do? Let's use another material than water to produce electricity. What is that? That is gas turbine system. So instead of vapor, let's use gas. Then what's the problem of gas? It doesn't undergo phase change. Then how can we obtain high pressure, high temperature without phase change? When you have a water, you just need to heat it. So liquid water becomes vapor, we obtain high pressure. If you have a gas, how can we obtain high pressure? We need to use compressor. Instead of pump, we are going to use compressor. So once we compress gas, it goes into combustion chamber or heat exchanger where we obtain high temperature heat. Goes in. So it increases pressure and temperature even further. Then it goes into turbine to produce work. So this is gas turbine. Sounds good. Then what kind of, the working gas we can consider? There are many different working gases are considered, such as carbon dioxide, helium, or high pressure sodium, or there are many different, the gases are studied nowadays. Then, what is the good thing about using this gas system? What is the maximum temperature? Much higher than water, so we can improve the thermal efficiency. So we can achieve much higher temperature. So the thermal efficiency goes pretty high. So that's good. Then what is the drawback of gas turbine system? This one, the cost is low. This one, cost is very high. So that's the drawback. What do you mean? We use them. We use them in real world.
But don't the government
For what?
government doesn't like government.
So, the government subsidies is, it's not about only technical decision, it's a political decision. So I'm not going to discuss that because I don't know very well about that. So the main difference is that water has a temperature limit because of the phase change. So if we want to use gas system, we need to rely on compressor, and this one costs a lot. But if we use this compressor, we can improve the thermal efficiency. So it's more like a balancing game. Okay? And where do we consider this most likely? In many power plants, different types of power plants. Not about fossil fuel power plant because fossil fuels are expensive. Then what else? Nuclear power plant. Yes, this is one of the hot area in nuclear power plant. Why is that? Don't we use, the water-based nuclear power plant? Yes, light water nuclear reactor, heavy water nuclear reactor. So we use water as the working fluid. And the problem is that, what is the temperature, exit temperature of the nuclear reactor? It's very high. Increasing temperature is not a problem. We want to limit the temperature, right? For safety. So if we use water, we need to bring the temperature down to maybe 300, 400 degrees Celsius, the maximum temperature of the water. So it decreases the thermal efficiency. So if we use a gas turbine, we can increase the inlet temperature of the turbine, not about 400,000 or the 2000 degrees Celsius, whenever the material can withstand. So we can achieve extremely high efficiency. Then why don't we do that? Of course, we are studying, but the main reason is going to be safety. So efficiency is not a problem in nuclear power plants. Safety is a problem. Don't you know about the Chernobyl in Ukraine or Fukushima in Japan? What happens? Temperature went too high, right? Another thing is that solar thermal power plants. So how can we obtain high temperature heat? You just need to install more meters. So reflector meter into the focal point. What is the maximum temperature we can achieve? Over 1,000 degrees Celsius. Can we use water at the temperature? No, we need to limit the temperature. So water limits the thermal efficiency. So if we use a gas, we can improve the thermal efficiency, but the problem is this one. Then let's talk about the problem. How much power this pump consumes from the power turbine produces? We can use one parameter to discuss that, back work ratio. So what is the back work ratio? How much power we use to run the pump out of the one that we produces? About 1 to 2% in vapor power plant. What is the back work ratio in a gas power plant? 20 to 80%. So that is the problem. Still, we can achieve very high thermal efficiency. So it's again another balancing game, right? Then let's study gas turbine system. Can we use thermodynamic equation to analyze this gas turbine? Yes, there's something called air standard Brayton cycle. So typical Brayton cycle consists of compressor. So this is the problem, costs a lot of power. And we have a heat exchanger where we obtain high temperature heat, and this compressor consumes power, WC, and it goes to turbine where we produce power. Turbine power, W dot T, and these two are coupled together so that some of the power this turbine produces is going to run this compressor. So in reality, there's a air and fuel goes in, go to combustion, and comes out, exhaust gas will be released. But in air standard Brayton cycle, for simplicity, we are going to introduce another heat exchanger where we reject any waste heat so that it can be a cycle. So the inlet of the compressor is going to be always number 1, 2, 3, and 4. So we can apply energy balance equation for each component. And let's see how we can do that. It's actually very simple. We are going to assume kinetic energy change and potential energy change is 0. So it's going to be only energy transfer by mass or work or heat. So what is the energy transfer by mass? Simply m dot h1, m dot h2, m dot h3, m dot h4. So let's come up with energy balance equation for this compressor. The general energy balance equation, assuming the kinetic energy, potential energy are neglected. And by the way, this is an open system. Inlet, exit. So we have one inlet, one exit, so open system. Energy balance equation is the sum of energy transfer in should be the same as the sum of energy transfer out. So let's talk about this compressor. How many energy transfer entering this compressor? 1, 2, here, 2 arrows. So W dot C is m dot plus m dot h1 is going to be 1 out, m dot h2. So this is one energy balance equation for compressor. What about the heat exchanger? 1, 2 goes in. Q dot in plus m dot h2 is m dot h3. What about turbine? 1 goes in, 2 come out. M dot h3 is W dot T plus M dot H4. What about this heat exchanger? 1 goes in, 2 come out. M dot H4 is Q dot out plus M dot H1. So these are the energy balance equation. How do we determine the thermal efficiency? The thermal efficiency can be determined by desired output, required input. So W net over Q in. So how do we determine W net? Turbine power minus compressor power. So turbine power, if you move this one to the left-hand side, we get M dot H3 minus H4. Oh, so W dot net is going to be W dot T minus W dot C.
Oh.
So let's calculate W dot T right here. So move this one to the left-hand side, we get W dot T. What about W dot C? C. Oh, yeah. H2 minus H1. M dot H2 minus H1. Q dot in here, moving this one to the left-hand side, right-hand side, M dot H3 minus H2. Then what do you want to do? Cancel M dot out. Then you get the thermal efficiency. One last thing is going to be back work ratio. How do we calculate back work ratio? Very simple. How much compressor power we consume out of the turbine power that we produces. So compressor power here, M dot H2 minus H1. How much turbine power here, moving this one to the left-hand side, M dot H3 minus H4. And you can cancel M dot out. So this one slide shows everything about gas turbine. Any question? Yeah, we assume that steady state open system. Then whatever goes in should go out. If you maintain your weight, whatever you eat, you need to put out, right? Well, VWR, back work ratio, how much compressor consumes out of the power that you produces. So this one produces, let's say, 1 megawatt, and this one consumes 0.5 megawatt. What is the back work ratio? 50%, 0.5. Make sense? Yeah. Okay, so $20 per page. I was kidding, but I still need that. So no, I cannot take that. I cannot take that. I'm gonna lose my job. I don't want to lose my job for $1. No, I don't want to risk my job. I like my job. It's the easiest one in the world. Think about, that there are so many engineers with PhD, why they want to come to school, even though the pay is half of, what you get paid outside. Because outside, how many times that you need to work? You need to work for your boss. Who's my boss? No one. So I can, make my own schedule, as long as I show up in your classroom. About the class schedule? It's more like, that we need to negotiate because if I change my schedule, it's going to change someone else's schedule. It's going to change someone else. So it's like a domino, right? Pizza. Maybe one time per semester. I canceled one class this semester, right? Yeah. You don't remember? Okay, so let's solve a problem. This is the last slide. So within next 10 minutes, we can go home. Or we can discuss the final exam, okay? One thing you can notice here is that this is called cold air standard analysis. This cold air standard analysis means that in the previous Otto cycle and diesel cycle, how did we determine thermal properties such as U or H? We had to use table 822. But if it is a cold analysis, we are going to assume constant specific heat. If you assume constant specific heat, you don't have to use table 822 anymore. If you want to determine, let's say, H2 minus H1, it's going to be Cp T2 minus T1. Isn't it nice? So whenever you see cold air standard Brayton cycle, by the way, in chapter 9, we are going to use cold analysis only for Brayton cycle because Otto cycle and diesel cycle, we have table 822. Okay, of course, assuming constant specific heat comes with another error. So this one is less accurate compared to just standard air standard cycle. So let's solve this problem. Air enters a compressor. So we have compressor. And we have heat exchanger. And we have turbine. And we have heat exchanger. This is the simplest Brayton cycle. We provide compressor power, W dot C. It produces turbine power. It consumes. There's a heat transfer into this heat exchanger. There's a heat rejection, Q dot out. So we have number one. Number one is the inlet of the compressor. Number two, number three, and number four. Okay? Then, what do you want to calculate? The thermal efficiency of the cycle. The thermal efficiency of the cycle, right here. The thermal efficiency of the cycle is H3 minus H4 minus H2 minus H1 over H3 minus H2. Yeah, it cancels out. And back work ratio, B, back work ratio is H2 minus H1 over H3 minus H4. Okay? Net power developed is this one. The one in the numerator. The net power W dot net is going to be W dot T minus W dot C, which is M dot H3 minus H4 minus M dot H2 minus H1. So we can use this heat transfer heat equation. This one becomes thermal efficiency Cp T3 minus T4 minus Cp T2 minus T1 over Cp T3 minus T2. Then what's going to happen? Cp cancels out. You just need to know the temperature at each state. Then you determine the thermal efficiency because it's cold air standard analysis. So what is the temperature at 1? Air enters the compressor at what temperature? Yeah, 300. So this one is 300 Kelvin. The turbine inlet is 1400. The inlet is number 3. So this one is 1400. This one is 1400. So we just need to determine T2 and T4. How? Our assumption is this compressor is isentropic compressor. This turbine is isentropic turbine. So entropy remains constant. If isentropic, entropy remains constant. So S1 is the same as S2. S3 is the same as S4. When you have an isentropic process and you can assume constant specific heat, there is one equation that you can use between temperature and pressure that you studied from where? Chapter 6. So in chapter 6, for isentropic process, T2 over T1 is T2 over P1 to the power kappa minus 1 over kappa. That's not K, that's a Greek letter kappa. Anybody from Greece? No one? So I guess that's kappa. I don't know how to spell that. Kappa, right? We can name anything. So between 1 and 2, entropy remains constant. So if you know the temperature at the inlet, you can determine the temperature at the exit as long as you know the pressure difference. Then do we know the pressure? Let's see. What is the pressure at the inlet? 100 kilopascal. What is the pressure at the exit? We do not know the pressure at the exit, but we know the compressor pressure ratio, which is 10. Okay, so 10 times 1000 kilopascal. What is kappa? 1.4. 1.4. What is the inlet temperature? 300 Kelvin. Can you determine the exit temperature? Yes. So what is the exit temperature? 579.2 Kelvin. Wait, we can do the same for the turbine. It's also isentropic process, right? So let's apply the same equation. S3 is the same as S4. So we can say T4 over T3 is T4 over P3 to the power kappa minus 1 over kappa. What is the compression ratio? Again, 10? No, that's the other way. This one is 1000 kilopascal. This one is only 100 kilopascal. So this is 1 over 10. And kappa is 1.4. This is 1.4. What is T3? 1400. So can you determine T4? Yes. T4 is 725.13 Kelvin. Then T2 is what? 579.2. 579.2. What about T4? 725.13 Kelvin. Can you determine the thermal efficiency? Yes. The thermal efficiency is 0.482. What about back work ratio? Back work ratio can be determined by this one. H2 minus H1 is a CP T2 minus T1. CP T2 minus T1 over CP H2 H3 minus H4 T3 minus T4. So CP canceled out. Do we know T1? Yes, 300. Do we know T2? 579.2. T3, 1400. T4, 725.13. Can you determine the backwork ratio? Yes, backwork ratio is 0.4137. So about 41% of the power that we produce by the turbine is going to be consumed by the compressor. Finally, the net power developed. W dot net can be determined by this one. M dot CP T3 minus T4 minus M dot CP T2 minus T1. We already know T1 300, T2 579.2, T4 725.13, T3 1400. Specific heat, you can find it from a table 1.005, 1.005, M dot. Oh, do we know M dot? Oh, 6 kilogram per second. So we have everything. Can you determine the net power developed? Yes. 2385.9 kilowatt. That's how you solve this problem. Okay? Any question? That completes thermodynamics. That was simple because it's what? Cold air standard analysis. If it is cold air standard analysis, we are assuming one more thing, constant specific heat. As long as you use specific heat, things are very simple. However, since you're assuming constant specific heat, which is supposed to be a variable specific heat, so it comes with another error. So I recommend to use table 822 rather than using this cold air standard analysis. Okay. Cold air standard? No, I'm going to use just air standard analysis. So you cannot assume constant specific heat. So the problem that you're going to see in the final exam is going to be similar to problem in the Otto cycle or diesel cycle. I know that you have many final exams in that week. So let me simplify how you your work. So chapter 9, there will be no problem related to a gas turbine. So it's going to be only either Otto cycle or diesel cycle. That save your time, right? And so, by the way, any question about this particular problem? I don't think so. This is the easiest one, right? So let me give you a summary. So 20, 20, 20, 60. I'm going to be millionaire. Okay. So in the final exam, I think we had a discussion that the final exam is going to be 1 hour, right? Tuesday, 2 o'clock, 2 o'clock. Yeah, 2 p.m. So you will see 3 or 4 problems on our exam. We had a discussion about that because I consider each problem takes about 15 minutes. So if it is 1 hour exam, you see 3 or 4 problems. If it is 2 hour exam, 7 or 8, 3 hours, 11 or 12. And you agree that 4 problems are okay, right? So 1 hour, not 2 hour, okay? 1 hour, 3 or 4 problems from chapters 6, 8, and 9. And you will see 1 problem from chapter 9. It's gonna either Otto cycle or diesel cycle. One of them, just one. 1 problem from chapter 9. 1 hour. Hour 15, then I can update that 4 to 5 problems, 1 hour 15. Okay, going back to 3 to 4. Or you can do just 15-minute exam, 1 problem. That's too risky. It's like investing coin, right? So 3 to 4, okay? So you will see 1 problem from either Otto or diesel cycle. Never use cold air standard analysis. Use table A22. And there's 1 problem from chapter 8 for sure. And we solved 2 problems in the classroom in chapter 8. I'm sorry. The simplest one, the easiest one, and the hardest one. So the problem that you are going to see is going to be somewhere in the middle. Then what makes the last problem in the previous chapter hardest? Because it has 2 isentropic efficiencies. 3 isentropic efficiencies because the turbine has 2 stages. So you may see less than 3. Maybe 1 isentropic efficiency could be enough. So 1 problem from that. I don't have to explain anymore because we solved 2 problems. In chapter 6, 2 items. Isentropic efficiency, like a turbine or compressor, or entropy generation. You remember we studied entropy balance equation and we solved the problem to determine isentropic efficiency, right? So if I give you 4 problems, you will see 1, 2, 3, 4. If I give you 3 problems, you will see 1, 2, and 1 of these 2. You can prepare 1 formula sheet, front and back, letter size. And if you have any question from today until the exam day, if you have any question, and if you're stuck in somewhere in your solution, take a photocopy and then shoot me an email. I will review and then get back to you with my comment, okay? So if you have any question, don't worry about that. Send me an email, okay? Any question? Give me about, no, cutoff day is gonna be Tuesday. But give me at least, a few hours for me to get back because I may be, yeah. But I will do my best to respond within a day. Any question? No? Okay, then, yeah. Yes. So the first Rankine cycle problem is the simplest one. The second one is the hardest one. Yeah. And we also did 2 problems in chapter 9, Otto cycle and diesel cycle. The problem you are going to see is going to be similar to one of them. Every homework, remaining homework is due by the exam date, so by 2 p.m. if you miss any previous homework, you can still submit that, but the deadline is 2 p.m. on Tuesday. If you submit late, if you the submit the previous homework which is already late, you will get 20% penalty. But there is no homework submission after 2 p.m. on Tuesday. Okay,